This video describes pre-orthokeratology analysis that you can do with the Medmont E300 corneal topographer. Start by selecting your baseline pre-orthokeratology topography. Go up to Display and Axial Power. This allows us to view, is it with the rule? Is it against the rule? Is it oblique? We can also look at the type of astigmatism, whether it's apical or limbus to limbus. In this case, we see a figure eight or hourglass shape confined to the apex of the eye. This is what we refer to as apical astigmatism. As we go farther out in contours, we notice the green-yellow border appears to make an almost concentric circle, indicating the astigmatism is coming to an end. So this is your apical astigmatism. This is a patient that does very well in symmetrical orthokeratology lenses, in other words, non-toric orthokeratology lenses. We can switch over now to the tangential map and see that the displacement of this eye, the contours, the green-yellow border, appears to be pulled or stretched a little bit inferior and a little bit temporal on this left eye. So we know that placing an RGP on this cornea is most likely going to want to ride following that corneal displacement, a little bit inferior, a little bit temporal. Another thing we could do is look at the amount of corneal astigmatism under the Data tab, and we compare the flat and steep K, and our delta is 1.39. So this patient has 1.39 diopters of corneal astigmatism. Orthokeratology, we know, typically works very well when the corneal sill is 1.5 diopters or less. Now, let's look at sagittal depth, another way of determining how easy or how difficult this case may be. Let's go up to Analysis and Details. Then set your chord for the bearing point of your specific orthokeratology lens. In this case, the 11.0 millimeter lens that this practitioner uses bears at 9.35 millimeters out. In other words, the diameter of bearing of the lens, not the lens diameter, is 9.35 millimeters. We go down to the sagittal depth, the weighted average height. Click our cursor on the flat, and the software measures the height of the eye as 1,573 microns. Comparing that to the height of the steep, 1608, there's a difference of 35 microns between the height of the eye across the horizontal and the height of the eye across the vertical. When the difference between the steep and the flat is under 40 microns, that's typically where a symmetrical, non-toric orthokeratology lens works quite well. If the differential between the flat and the steep were greater than 40 microns, then we are most likely to require a toric Ortho-K lens. We could also look down at the Data tab at the eccentricity, and we see the flat eccentricity is 0.7. It has been shown that the higher the eccentricity, the better the cornea responds to orthokeratology treatment. The normal eccentricity, or the average of normal eyes with the Medmont, is 0.67. So this patient falls very much within the norm, if not slightly higher, should be able to achieve a good orthokeratology outcome relatively easily. So the higher the eccentricity, the better the potential for Ortho-K effect. Let's take another patient, remembering that this patient has this confined apical astigmatism. When we compare that to this patient, we see now an astigmatism that runs from one side of the eye to the other. That hourglass is very much limbus to limbus in diameter. The limbus to limbus corneal astigmat is much tougher in orthokeratology because the peripheral corneal shape is more astigmatic. That's more challenging from a fitting perspective or an alignment perspective. Centrally, to push the astigmatism out of the way in a limbus to limbus corneal astigmatism is tougher. So your apical astigmatism, much easier case in orthokeratology. Your limbus to limbus, more challenging for peripheral fit, and more challenging refractively to eliminate the central corneal astigmatism. Let's look at this patient another way. Again, we've looked at the axial interpretation, and we see that we have a limbus to limbus corneal astigmat. We switch over to the tangential. We look at the contours of the eye, the green-blue border. It appears that many of the hottest contours are stretched a little bit toward the higher side. So we might expect RGP lenses or orthokeratology lenses to want to position slightly superior. Let's go to the analysis and details window, and again look at the sagittal differential. We click our cursor on the center on the flat meridian, 1482, on the steep, 1507, a difference of 88 microns between the depth of the eye along the flat and the depth of the eye along the steep. We said that 40 microns was the threshold where a symmetrical lens will typically work. When it's greater than 40 microns, a toric lens is usually required. In this case, the patient measures 88 microns of sagittal differential between the two meridians. This is a case that would certainly need a toric orthokeratology lens. So use the axial interpretation to understand, is it apical or is it limbus to limbus corneal astigmatism? Use the tangential map to determine if the corneal cap is displaced, which may decenter slightly your orthokeratology lenses. Use the data tab at the bottom and look at corneal astigmatism. When it's less than 1.5 diopters or 1.5 diopters or less, typically a symmetrical non-toric orthokeratology lens will work quite effectively. When it's greater than 1.5, a toric may be required. Look at the eccentricity value. The higher the E value, most likely the better the case will be in terms of treatment. The higher the eccentricity, easier it is to create myopic reduction. The lower the eccentricity, the more challenging it is. Then use the analysis and details window to measure the sagittal differential between the flat and the steep to understand, is a symmetrical or a toric lens likely required? And if a toric is required, how much toricity would this patient need in microns to create a beautiful 360-degree alignment?